Now, at this point, you may suspect that this is very similar or a very similar process to what we were doing when we were running logit or multinomial logit regressions. And you'd be correct, you're onto something here. And that's because all of these different regression models are a subset of generalized linear models. And by that, we just mean that we are trying to transform essentially non-linear distributions through some sort of link function. So in the case of a logit regression, we're using a log function to transform the Bernoulli parameter into that linear association that could be expressed with our covariates, right? We are doing the exact same thing, but we are using a log function now and referencing a Poisson random variable here with parameter mu. So what this allows us to do is, given the fact that lambda can only be positive, right? It has to, given the restriction that we have for the fact that it's a count variable. So even if we had k or x equals 0, lambda would still be positive. Now, what this means is that if we use a log link function, we can then transform this random variable and express it throughout a domain from negative infinity to infinity, just like we would in a normal least squares situation, which is what we want to do. And like I said, I've been calling these functions that we use to connect our logistic model or our Poisson model into a linear association between our covariates and our outcome. I keep calling these link functions, again, because they are the connective tissue between our outcome and our linear expression of covariates. So in this modeling, we are assuming for the Poisson model that the log of this lambda parameter is linearly related to the independent variables. And that means that the mean and variance are equal for any given value of this lambda. In order to estimate this model, we're going to use an iterative process called maximum likelihood estimation that is essentially going to use calculus to slowly approximate a likelihood function with the goal of minimizing it, just like we did with regard to, we are going to maximize it, obviously, because we're trying to climb to the mountain. But what we are doing in the process, right, is we are trying to create better model fit here. So it's the same type of process that we are trying to think of or institute with regard to least squares, right, where we're trying to minimize the squared error. In this case, what we're trying to do is, again, since we can express the linear association of our covariates with our outcome using a likelihood statement, in this case, a log likelihood equation, we would then try to maximize that given our set of data. And we would do that in an iterative process that we call maximum likelihood estimation. Now, I really don't want to get into this because, one, this is complicated, and two, this is an entire course that you could get into if you are interested. So I'm going to kind of punt on this topic, and if you want to learn more, I've included my e-version of the kind of gold standard book on MLE. And if you're interested, check it out. I would normally lend this to you, but obviously circumstances don't dictate that this semester. But now that we've talked more about the background of these generalized linear models, we're going to delve back in specifically to the Poisson model and go over an example.